Okay. Okay, today is kind of the culmination day of 3 days worth. So yesterday we talked about yesterday we talked about how there's like a fight for electrons, right? And I've been constantly using this example of like me stealing Sarah's lunch money, right? And so,
Why are you stealing my lunch?
sorry, I stole Balka's lunch money. Okay, so I want to steal Balka's lunch money. Okay. Now, if I was the stealer of electrons, would I be the oxidizing agent or the reducing agent?
Reducing agent.
Well, you got a 1 and 2 shot at it. If I'm going to be the person who steals Balka's money,
Oxidizing agent.
let's talk through it then. Okay, so have your answer in your head. And we'll see whether you have it right. Okay. Okay. If I am the person who's stealing, I'm causing him to lose. Does that make sense? So that means that I am the person who causes him to lose. Well, losing is the loss of electrons. That's oxidation. So he would be oxidizing. Therefore, I would be the oxidizing agent, being the one who causes him to lose his electrons. So we said oxidizing agent. Good for you then. So if I'm the oxidizing agent by the one who's stealing the electrons, then by default, Balka, the one giving them away, would be the reducing agent. Reducing agents cause somebody else to reduce. So if I'm reduced, I'm gaining electrons. I'm stealing Balka's lunch money. So if I'm the one who's gaining extra money, then he's the one who caused me to gain money. So he's the reducing agent. So, long story short, yesterday in the notes, I would have shown you a little picture, which I screwed up at first. It was reducing agent to oxidizing agent, and the arrow says that electrons go from the reducing agent to the oxidizing agent. So, but someone really clever came up with this concept here. What if rather than me just stealing the electrons directly from Balka, what if we could run them through a circuit? And that's what I've been building up to for 3 classes. So rather than me taking them directly, what if we went around and flowed through, like from you to you to you to you around to me? Then what you could do is in the middle of that, you could turn on, say, the light bulb. So look at the picture that you've got here. You guys all know how like a circuit works? Basically, it has to be one continuous loop. You would have like an electrode here, and then maybe the electrons might start flowing here, and then through this piece of metal here. And of course, my board just broke. I'll put it somewhere else. Well, it loses connectivity for some reason. Like it starts to connect, and then it just kicks me out. It works so good until it decides to just stop. And then if I like reset the battery, then it works.
Don't you have
I do, but I don't want to have to bring a wire all the way over here. So, okay, so where was I when I was drawing this here? No, it's not working. Okay,
it goes through the wire.
fighting for electrons, eh? All right, let me take this from the top here. Let's say that right here, this guy is going to lose electrons. If this guy's losing electrons, this piece of metal right here, you guys well with me?
Yep.
If this guy's the one losing electrons, what is he, the oxidizing agent or the reducing agent? Yeah.
Wait, no,
if he's losing electrons, that was Balka. Balka is the one giving me the money, so the reducing agent gives away electrons. And then the electrons would have to run through the wire, so they'd like run through the wire. But if along the way of them going to the oxidizing agent over here, rather than taking the short little distance and just going like this, if we were to separate them, see how these two pieces of metal right here are not actually directly touching? If they were literally touching each other, they'd go right from here to here. That would be really boring. No battery would occur. But if we were to separate them by putting them into some sort of spongy-like material, I'll show you what we use in chemistry later, then the electrons run through the circuit. Well, partway through, it could get interrupted by some sort of machine, right? In this example, a light bulb or your cell phone, your calculator, anything that runs on battery power, right? It's actually really clever. So rather than taking the direct path of going from reducing agent to oxidizing agent, take the long path.
Can't you make a battery out of potato?
Exactly, actually. That's what this one right here shows really well, is if you put 2 pieces of copper and zinc, I think usually work well, into a potato, you can make a battery out of one of those things. Because really what ends up happening is either the copper or the zinc ends up stealing / losing the electrons.
So you can't have 2 of the same metal?
No, you need to have one to steal electrons and one to give them away. So like you couldn't have copper give to copper. And actually that's a good thing to talk about here. It has to fit based on this table here. You'd have to have like this copper right here try to steal this aluminum's electrons. Hmm. Well, nuclear plants, they would run based on splitting of atoms that would then heat up water, which they used to run a turbine. So that's probably not the same sort of thing, unless there's something more specific you're thinking about.
Isn't a nuclear bomb just chemical?
Yeah, a nuclear bomb basically involves the fission or the fusion, but that's a little bit different than the. I mean, it does involve chemicals, but it doesn't involve this sort of chemical reaction. No, no. It involves taking two nucleuses and putting them together or splitting them apart. Well,
How do
anyways.
you do that?
Why don't I talk about that later here?
I love how we get to talk
Just
about
so distracted.
nuclear
That's okay.
bombs.
It's a good question. Maybe I'll talk about it later though. So, okay, here's some words I want you guys to know. Then you guys can read. You guys can read.
No.
Electricity is the movement and flow of electric charge. What is the electric charge? Like, what is the item that moves?
Electrons.
Yeah, electrons. Yeah, and
That's
so
why
normally.
it's called electricity.
Exactly. So I usually use a little e with a little negative sign to represent electrons. It's a short little notation for electrons. Why can't the protons move? Good. There's one good reason why. If you change the amount of protons something has, then it goes from being copper to nickel to cobalt. You can't move electrons or protons. The other reason why is the protons are stuck in the nucleus, right? And the nucleus is really tightly packed together in the middle, whereas the electrons are free flowing. They have the ability to move. So that's electricity. Now, electric charge can be positive or negative, which may seem strange because you're like, hang on, didn't you just tell me that you can't have positives? But you know the way in which you get a positive charge cause something to lose its electrons. Yeah. So you can have positive or negative charge. In case it ever comes up, the unit for electric charge is coulombs, which is measured with a capital C. Essentially, a coulombs is rather than measuring things. Sorry, the capital C is the unit for coulombs. You're right. Q is the letter. You can also use a little q actually. Sometimes you'll see a capital or a little q. I'm distracted now. That's okay, good. Made a good point because I did say it wrong. You know how when we measure atoms, we don't measure atoms one at a time because that would be kind of ridiculous. We measure them in a mole at a time. Well, we measure them 6.02 times 10 to the 23 at a time. A coulomb is very similar. It's basically just measure a whole bunch of electrons at once. So rather than counting them 1 or 2 or 3 at a time, it's like you're counting them 10 billion at a time. Does that make sense? So, another definition I want you to know is called an electrode. An electrode is the location of the buildup of positive and negative charge. And you guys can see that on here, these two little metal tabs are the electrodes. One of them is going to lose electrons and become positive. One of them is going to gain electrons and become negative. And I'm sure almost all of you have some intuitive knowledge of a battery, right? Like if I were to draw like a car battery, just like your basic box sort of thing, right? You've got one electrode that's like the positive one. You've got one that's the negative one. I mean, if anyone's ever jumped a car before, you understand, okay, we'll hook this one up with this one. Don't reverse them.
Don't touch them.
Don't touch them. That'll cause, well, what happens when you touch them? What is that causing to have happen? It completes the circuit. And so basically what ends up happening is when you get really, really, really close, electrical charge is jumping from one to the next, completing a circuit. Yeah, and you wouldn't want that to run through your body, so you definitely don't want to have it touch you, right?
So. Because isn't it if you touch the metal, because your body's able to touch it, you can let it.
Yeah, it could end up happening that way, so you gotta be careful. Oh, goodness. All right, let's move forward here. Some more definitions I want you guys to know. Current. You guys ever heard the word current? Current is measured in amps. And current is the stuff that if you have too much current, that's what kills you. So like your heart can only take so much of that. I think that's what they end up trying to do when they're restarting your heart is they're trying to apply a current across your heart to re-shock you back to life. So current is what causes the problem because it's how much charge that moves per second. When I explain this to my chemistry or physics kids, I think of it as like how fast the electrons are moving. If you have electrons running through the circuit and they're taking their sweet time going around the circle, that's not going to kill you. That's going quite slow. But if those electrons are going quite quickly, that's your current. So current in a way is like the speed at which your charge moves. But don't forget, this Q right here for charge, that's how many electrons, but in like a big grouping. It's like buying your electrons 10 billion at a time. So 1 amp then is basically like your coulomb, your 10 billion electrons, all moving in 1 second. 2 amps would be 2 billion electrons per second. That's all. Okay, another definition I want you guys to know is voltage. Voltage and current, a lot of kids will sometimes use them interchangeably, but they do mean different things. Voltage is how much energy change you have. When you guys use a battery, you would need to have like a 12-volt battery or an 18-volt battery or something like that to maybe run your car. Your house runs on maybe like 110 or 220 volts to run your washing machine or something. You've heard the word voltage before? The batteries in your calculator are probably 1.5 volts.
Voltage how much?
It's not how much, because the much is actually the current. The current says how many electrons are zipping around per second. The voltage says how much. Yeah, voltage is more like how much energy do they have.
Because I just remember last year using the thing of the river.
I'm going to do that on some of my next slides, actually, yeah. Okay. So when it comes to voltage is how much energy they have. Now think about this for a second here. Your calculator needs AAA or AA batteries, which are usually 1.5 volts. Whereas like your car needs like a 12-volt battery. That kind of makes sense, doesn't it? Doesn't your car, it doesn't need more energy to run than your calculator does, right? But current is like how many of those electrons are zipping around per second. So there is a difference between the two. Long story short, I need you guys to know that a battery moves electrons for what's considered to be something with a high potential to a low potential. It always goes from high to low, which kind of makes sense, right? Like a river would run from high to low. Here's the analogy that I sometimes use with my Physics 30 kids. So I thought this will work with you guys. Imagine that you have a water tank above the ground. Okay? And like just, one of those old-fashioned where they store their water for the city kind of thing, right? And
water tower?
Exactly, a water tower. Okay? And you end up having like a little puncture in the bottom of it, and water is going to start flowing out. In this analogy, water would be like your electrons. Okay? Your current would be based on the size of the hole that the water is gushing out of. If you had a little pinprick and the water would just drip out one at a time, there's not a lot of current. It's slowly, like one drop at a time making its way through. But if I were to like put a big gushing hole through and the water is just pouring out, that's your current. Well, I mean, as the water pours out, it would rip the sides off a little bit. Okay. Voltage, however, is a little bit different. Voltage is based on how far the electrons have to fall. So if the electrons have to fall this far, versus, let's say the water tower was like way up here. Say the water tower was taller. See how they would fall further? That's what voltage is. So voltage is how much energy they would pick up. So if I were to drop my pen from here to here, it would only pick up, that much energy. If I were to drop them from here to here, see how it would pick up more energy over the course of doing that? So current is like how many of these electrons can kind of go gushing through at a time. And we measure them in coulombs, which is basically a lot of electrons. Okay? So an amp is a whole bunch of electrons per second. Your voltage is how much energy can those electrons get as they travel from here to here. So your 1.5 volt battery doesn't really give you a lot of energy, whereas your 12 volt battery gives you way more energy. Your household appliance that like your dryer that runs off 220 volts, that uses way more energy. Fair enough? It's kind of the same thing with this picture then here. The voltage of the battery is like how much energy it takes for this electron to go all the way around the circuit and back around again, how much energy it has. Okay, a little bit of history. Batteries have actually been discovered for at least a couple hundred years, if not before that. I watched one episode of, you guys ever watch Mythbusters? Ever see that show? They were running an experiment to see whether batteries might have been used during like ancient Egyptian times using clay pots and lemon juice. They were trying to figure out whether or not they might have existed back in like, I don't know, Cleopatra, Nefertiti, I don't know, King Tut type days. But here's the first guy we know of who like made a battery that we'd consider pretty scientific. It's Alessandro Volta, and we named the Volt after him. I mean, even Chevy names their car after him, right? Volts. So basically his concept was that he made a whole bunch of small little beakers attached to each other, one to the next, to the next, to the next, and they were known as piles because you kept piling them on top of each other. And yeah, this is basically a prehistoric version of the battery. Now, we'll make ours in beakers on Thursday. His, I believe, looks something like this, where you basically just connected one to the next to the next. So, um, electric cells are often. Oh, sorry, I should point this out here. If we ever talk about a cell in biology is like has a nucleus and mitochondria and stuff like that. A cell in chemistry is a fancy word for a battery, by the way. So if we ever talk about a cell, which I've got on this slide right here, cells are batteries. So other words you might know are the words galvanic cells or voltaic cells. Those are just fancy word for batteries. Okay? So these are batteries. Okay, well, how do you make a battery? Well, as Volta discovered, you need to have two electrodes. Why do you need two? Why can't you just have one? More than just that, you need someone to gain electrons. You need someone to lose electrons. That's why you have to have two of them, right? We can't have a bullying situation for money with just me, right? I have to steal your money. There has to be two of us, the bully and the bullier and the bully. You know what I'm saying here? So you always have to have two. You have to have two electrodes, and we have names for those. They're known as the anode and the cathode. So here's how you can remember how they work here. Anodes are based on anions, and they'll be negatively charged. Good. Cats have pos. Cathodes are based on cations, so they're positive. So the anode is the negative side of the battery, and the cathode is the positive side. And I'm sure you guys have seen a battery at some point in your life, right? They usually clearly label a positive and negative side. That's the definitions we give. So this I found somewhere. I never learned this in school, and so this never stuck with me. But to remember what happens where, this was the silly little, like, a Leo says grr kind of analogy. This is the one. It says red cat. And a red cat means that reduction is what happens at cathodes. I don't know. If that helps you memorize it, that works. And then the other one is that an-ox is the other silly little saying, which means that anodes have oxidization. I never learned that. I'll show you what I learned, and it might stick with you just as silly, because this is silly the way it was. But remember how we did Leo says gur? My teachers taught me that Leowa says gurk. It's dumb. Rather than Leo saying gurk, Leo saying gur, Leowa says gurk. My high school chemistry teacher taught me that. I have never forgotten it, because it's that dumb. But like, it sticks with you. The reason why you need to know this is you have to know whether the anode is the one that gains or loses electrons, or whether the cathode is the one that gains or loses electrons. Well, if you can remember these sorts of silly little things, now you'll know. The loss of electrons, which is oxidation, happens at the anode. Therefore, the anode is the thing that is always losing its electrons. So in my bullying example from earlier today where I was stealing Bauke's lunch money, Bauke would be the anode because he's the one who's losing electrons. But rather than giving them directly to me, he's going to run them through a circuit. And so then if I'm the one who's gaining electrons, I would then be the cathode. So cathodes steal electrons from anodes, basically. Here's another way I remember that. Anodes give their electrons to cathodes, which A comes before C in the alphabet. Anything that you can do to help you remember this, because this section is all like memorization of definitions and theory type stuff. There's no math to this. So. Okay, let me show you a picture of a battery, and then I'm going to show you a simulation of a battery I found online, and hopefully I can help explain what's happening here. So this is like a very, very crude battery. This is not like the polished version that you'd have inside your iPhone or your car or your even just like a good old Duracell AA. But this would function as a battery. What you would have is silver, piece of solid silver metal right here, and then a piece of copper metal right here. And what's going to happen is the silver and copper metals are going to engage in a fight for electrons. And in order to figure that out, I need to go back a few slides in my notes here. So, okay, this one's 66, just so I know where to come back to. Do you guys remember this table here from yesterday? Where is it? There it is. You guys remember this table right here? Okay. The battery you were looking at here was silver and copper. So I'm just going to erase what's currently written here. Silver is right here. And then here's copper. Now I know they are super close to each other, but it doesn't matter. In the world ranking, who is the better electron thief? Silver. Yeah. So what ends up here happening is silver, silver is Ag. Silver is going to try to steal copper's electrons because silver is higher up than copper. Does that make sense? So now that I've looked at my table and I figured out that silver is stealing copper's electrons, let me go back to the diagram and try to explain how this battery works then. So right here is solid silver. And this solid silver right here is going to steal this guy copper's electrons. But rather than having them directly touch each other, we send it the long way around through this wire right here. Now what ends up happening is because silver steals copper's electrons, copper is no longer solid copper, it's lost its electrons. And what it does is it turns into copper 2+. Because isn't a 2+ what would happen when you no longer have your electrons? And basically what happens is this little piece of metal, it corrodes away until it kind of like disappears. Right? And that's actually why a battery stops, is that either your anode or your cathode kind of like runs out because all of the solid metal here has been oxidized away, and you can see how these copper ions are coming off of there. Okay. Well, at the exact same time over here, this silver now has picked up more electrons, and there's a whole bunch of electrons extra on the surface of silver. Well, sometimes once the battery's been running for long enough, that becomes a bit of an issue because more electrons want to travel this way here. However, if there's already a whole bunch of electrons over here, don't electrons repel other electrons? Why would this electron right here want to go through the surface to come over here to where there's more electrons? Electrons don't like being by other electrons. So it becomes a bit of a problem if you were to always have all of that charge just building up here. So what you have to do in your battery is you have to have like a positive ion in this solution right here. And you can see that right here there's like an Ag+ ion. What you do is you put Ag+ there to begin with so that the plus can pick up the electrons. What it does is it coats the surface of the silver right here with a metal, and it uses up the electrons. Because otherwise, if there's too many electrons here, well then why would these guys want to come join the party? Maybe an analogy I've used before, if this kind of makes sense, is this would be like a party over here, and the electrons might be, I don't know, let's say boys at the party. And you discover that this party right here, there's all boys and there's no girls. And then another electron wants to come. And he says, well, why would I want to come to this party over here? None of the girls are at this party. It's just all the boys at this party, right? And so the electron would say, well, why would I bother coming over here? So what you really need to have happen is a silver, like a positive, to come take this electron away, and another silver positive to come take that electron away, so there's not so many electrons over here, so that then more electrons would actually want to come and join the party. I don't know if that analogy fits or not. So what ends up happening is this electrode right here wastes away, and this one right here builds up extra mass on it. And in the meantime, you can run like a device off of the current that goes through there. There's actually one more thing I do need to talk about, though. It's this little U-shaped tube right here. This is known as a salt bridge. What can also end up happening then is a similar issue. See how this guy right here, as the electron was being lost, it was also kicking out a positive because the copper was basically losing 2 electrons, but it was making a copper 2+ as well. This beaker is now becoming very positive. As all the electrons, as all the negatives go this way, this beaker becomes very positive. That also causes a problem because similar to like my party example, why would this negative electron want to go over here where there's more electrons? Electrons don't want to be by electrons. Electrons want to be by positives. Hey, look, there's a whole bunch of positives in this beaker right here. Does that make sense? So you have to counterbalance it as well with this little U-shaped tube. What you end up doing is you put another material in there that's not silver and not copper, and the most common one we use is sodium nitrate. I can get into the reasons why, but just go with it. The reason why is that the nitrates will then come through the salt bridge and pick up all these positives right here, which means that now this electron right here, there's no positives left behind to kind of call it back home because this negative right here came to pick up this positive right here. So then it's free to go through the rest of the circuit. So let me show you using the simulator how a battery would work then. So I just need to start from the beginning. How do I reset it? Maybe I'll just reboot the page. Okay, so here's a basic setup here. You've got two beakers, and we've got like this little bridge in between it there. Can I move this? I can't move this. Okay, So the first thing we gotta do is pick some metals to be our electrodes. So I've got silver, zinc, copper. I'll just pick zinc. See how it's gonna make a little thing out of zinc here? And then I'm gonna pick another metal, which might be, now I can't pick zinc again because zinc really is not going to lose electrons to zinc because there has to be like a fight for the electrons according to that table. So I might pick, say, copper. So now before I go any further, we go back to that table I showed you there. If we're going to talk about zinc and copper, who's the one that's going to steal the electrons? Yeah, copper's higher on the table than zinc. So that should mean that copper is going to try to steal zinc's electrons. So I'm expecting that the electrons are going to get built up on this copper electrode right here. Does that sound good? But even right now, if I click the little button here and I turn it on, I don't think it lets me turn it on yet because I haven't reached all my stages yet. It doesn't work because if the electrons tried to leave and go through the circuit over to here, you'd have that same problem. There's too many electrons over here. So why would this guy right here want to have more electron? Why would you want to follow? Because the ratio is not in your favor. That makes sense, right? So in this beaker right here, you have to put a solution. And typically what you do is you put in the same kind of solution you make it out of. So if you make this out of zinc, you'd make the solution out of zinc. And if you make this solution, if you make this out of copper, you make this solution out of copper as well. And that should now work. Now I'm going to flip the power source on. And now we can literally watch the electrons. See how the electrons are getting drawn up out of the zinc. And they're going over through the wire towards the copper. But watch what ends up happening. These copper 2 pluses come pick up those electrons right there. These positives take away these negatives, because otherwise these negatives would not want to keep following. Does that make sense? Further to that, over here, see how these negatives right here, they're kind of spitting out. I have to start again. It's lame. What we're doing again, it was zinc, zinc, copper, copper, go. Okay. So watch the zinc right here. As the electrons get sucked out of the zinc, see how positives kind of leave over here? That's what the salt bridge would do. In the salt bridge, a positive would kind of go towards here to make up for the fact that this right here is becoming really negatively charged. And the negatives would come over here to try to make up for the fact that this beaker is becoming too positive. So you actually do complete a circuit. You know how a circuit's actually supposed to go all the way around? Well, the circuit gets completed even though these two pieces of metal don't directly touch each other. Ions still actually end up having to flow through this little tube here, so that it actually does go all the way around. So it's actually quite brilliant. So my hope is on Thursday we're going to make a couple of these cells, and I'll show you. And I just realized that last year I did something kind of cool. I took the clock off the wall, and we actually managed to get the clock on the wall to run for like 3 weeks using a battery that I made with just some chemicals in class. Which is kind of cool. Like we just set it on a table. I hooked up a couple of wires to it from here, and that thing normally runs on like just a single AA battery, And yeah, it ran for like 3 weeks, which is kind of cool. So I might try to do that on our lab and see whether I can actually power a simple device like a clock using just a couple of jars and a couple pieces of metal. So, who watches Breaking Bad? You did? There's a scene in one of the episodes where Walt ends up going out to the desert, and Jesse leaves the keys in the van turned on. You know the scene I'm talking about there? And they end up getting stuck out in the desert in the middle of nowhere, and like they have no way of getting back, right? Walt ends up making a battery out of just random chemicals that he found lying around. No, I think he was okay because he managed to get the van to start from it. So, anyways, this is what he was doing. He just took some random chemicals, kind of peeled them together. I think he found some aluminum foil and some stuff. So, if you have it on Netflix, I don't know if you can find the episode, but I'm serious, like go watch it. I thought it was really cool the first time I saw it because it was like, wow, he's actually doing some chemistry. This is like, it's not fake. So, I just don't think I could probably show Breaking Bad in class. So, because it's rated R. Okay. Anyways.
Try doing different metals.
On this one here? Sure. On the simulator?
Yeah.
Alright, let's try a different one. If we were to do...
Try like the highest one and the lowest one.
Well, it only gave me 4 options.
Well, like, so try silver.
Okay.
And then...
So silver. Now, doesn't really matter how high on the list they are compared to each other. The height on the list doesn't really affect whether it works or not.
Try some hydrogen.
Okay. So we can do the hydrogen electrode. What this is going to end up doing is it's going to make hydrogen gas, actually. Now this one's actually going the other way, it looks like. It looks like it's stealing the electrons from the hydrogen this way and causing the silver to go here, because I'm thinking that the way it would work is that silver is higher than hydrogen. Yeah, if it's going this way, it should be positive, and if I flipped everything, it was going negative. Negative just indicates the direction it was traveling. So if I were to flip these around, yeah, either way it works. It just, either the electrons go this way, right? If I were to change it around and put the hydrogen here, the HCl here, silver. Oh, that's a good question. Actually, let's talk about that. So let's do this one here first. So here you see this, it's the same number, it's just going the other way. Okay. So if I were to change the metal, can I do it? I have to turn it off first.
You have to let it run.
Oh, okay. What I could do is I could try changing the metal, or I could try like not putting a solution in there, and we'll see that. Hopefully, this will show you that if we don't have all of these things, you need to have 2 solutions, 2 metals. Well, it actually doesn't necessarily have to be. It's usually best if it is. So let's try one here. Let's turn it off. Okay, let's go with this one being silver, but rather than silver, let's put in like copper. Right. And then over here, let's go like zinc with zinc. Right. And then if I turn it on, it may not actually do anything. But if I change it to silver again, then do I have to start over again? What's my metal? Silver with silver, and zinc with copper. See how it's not actually doing anything? We actually do see that the copper ions seem to be attracted to the zinc, but like there's no actually electrons flowing through there. So it's usually best just to do it with the solution should be the same as the metal you're working with.
It's turned orange.
Yeah, it looks like what's happening here is a replacement reaction's happening where copper and zinc are trading places. You guys remember single replacement reactions?
Yeah.
The silver and the zinc are, sorry, the copper and the zinc are changing places, but because they're directly in contact with each other rather than separated, there's no like electrical current running through the whole thing there. So, oh wait, let me keep going here because I got more notes. There's a lot of pictures I got to show you here. I think this is the next one I'm up to, right? Now, you have to have what's called an electrolyte. And we've already used that word electrolyte. What is an electrolyte? If it's an electrolyte, it conducts electricity. And the reason why it conducts electricity is because it contains ions. So you know how when I was putting those solutions in the beakers there, you have to have, you have to have either 1 or 2 electrolytes. I'll show you a little bit later a type of battery that only has 1 electrolyte rather than 2. So you have to have an external wire. You have to have a wire going around it, right? And then you also have to have that porous boundary. The porous boundary, by the way, was that like U-shaped little tube. You need to have something that accomplishes that as well. So it's either known as a salt bridge or a porous cup. This is what I was talking about there. That was like my guy-girl party analogy. Polarization of a cell can occur where you get too much positive or too much negative in one beaker, and then the electrons don't want to move anymore because why would electrons want to leave the positives? Why would electrons want to join more negatives? So you have to try to prevent polarizing cells. So, okay, here's something I need to show you. This is a shorthand notation letting you know how a cell works. It goes, there's an item, then a line, then an item, then 2 lines, then an item, then a line, then an item. Okay? The way this notation works is it's a shorthand way of telling you what's in your battery. The first item is your anode. The second item is the solution your anode got put in. The third one is your cathode solution, and then the fourth one is the cathode itself. The way I teach my grade 12s to do this is that it always goes from anode to cathode because A comes before C. What does an anode do again? Gain or lose electrons? Lose. And if you remember the silly little thing, it's Lioa and Gurk. Loss of electrons happens in an anode. Gain of electrons happens in a cathode. So this notation is a fancy way of saying that this metal right here would have been copper. Copper would have lost its electrons over here to silver. But in this solution, you're going to want to have silver plus. And this solution here, you're going to want to have copper 2 plus. Just so that you can kind of replenish the ion supply. Otherwise, this over here becomes too negatively charged. Too many electrons over here. These guys don't want to follow, so you better have some silver plus to come over here. So this would start building up in terms of mass. You guys ever seen like a dead AA battery where there's like that white kind of stuff that starts building up around it? Yeah, that sort of stuff. That's really what's happening here is it starts to build up too much. And then sometimes if there's too much buildup around the anode or cathode, that also stops the battery from running. If there was enough buildup around here, now this is really clever here. See how all the buildup is underwater and the cord connection is up top here? You'd be fine. But let's say that the buildup started occurring up here and then around here and then it covered up the cord connection. Well, now the electrons might not want to move anymore and your battery's dead. So, okay, you cannot have a cathode though made of hydrogen. Hydrogen's on your table, but you can't have a cathode made of hydrogen because hydrogen is a gas. And you can't clip an electrode to gas. That just doesn't work. So we usually use a substance like carbon. Carbon gets used in place of hydrogen, that's all. Okay, here's the one beaker solution. This is what we're going to do in our lab. Rather than having two beakers, someone really cleverly discovered that you could just take the two beakers and put a beaker inside a beaker. And it saves space. Can you kind of see how right here I have two beakers next to each other? Well, just make this beaker smaller. Okay. And then take that smaller beaker and put it inside the other beaker. See how that makes it so it doesn't need as much room? This is known as a porous cup. And what ends up happening is similar to the salt bridge, your ions are able to flow through the porous cup. So your positives and negatives can transfer opposite directions. So your cell doesn't become too positive or too negative. So this is what we're going to do in our lab. Okay, so here's what I need you to be able to do. I need for you to either be able to draw me a picture of a cell or to look at a picture of a cell. A cell is a battery, right? And just tell me what's happening. So here I've got kind of the basic setup happening. Could we label stuff? So the first thing you got to do is you got to go to your data booklet and you got to find that table of who wins the fight. Who wins the fight between copper and zinc? Okay, so if you know that copper wins the fight, that lets you know that electrons are going to go from the zinc towards the copper. Okay. Which means that we should now be able to start labeling Lioa and Girk, the anode and cathode. Loss of electrons is oxidization. It happens at the anode. So this guy right here is the anode, which means that anodes are the negative part of the battery. And we know that all because the electrons were going from zinc to copper. And we know that electrons go from zinc to copper because we looked at our table and it tells us that copper wins. Does that make sense? So that's where you always start. Look at your table first. Figure out who wins the fight. Once you know who wins the fight, you know who's taking the electrons. Once you know who's taking the electrons, that's the loss of electrons is the anode. We would call this guy then the reducing agent. Because if this guy is being oxidized, he's the reducing agent. And then once you got that figured out, then it's just the opposite over here. Copper must be the one that's gaining electrons to reduce, which must means it's the cathode. So this guy is the anode of your battery. This guy is the cathode of your battery. And then the anode is negative. The cathode is positive. And then this guy would be the oxidizing agent. Does that make sense? One more thing, they may ask you to figure out the polarization of the cell. That may be something you could get asked about. I don't think I'm going to test you on it a whole bunch, but just so it's clear, if this guy is gaining electrons, it means that those electrons are going to soak up some positive ions, and it's going to make this thing right here build up in like mass around the outside of it. Whereas this one right here is losing its electrons, it's going to cause ions to like decay off of it. And so this electrode should become smaller, and this electrode should become bigger. The battery, therefore, then runs out when either you run out of anode, and you just have no more metal here, like this thing literally disintegrates, or this cathode right here might become too built up to gain any more charge anymore. Those are the two main ways I would stop a battery. So, you guys able to do that? Okay. Let's try another one here. Let's diagram and label this cell. This one's a little bit more challenging. I gave you the battery notation. So what does the first thing right here mean? The first bar was the anode. Yeah, it goes alphabetically. Anode. So it means that this piece of metal here is carbon solid. Now the only reason we use carbon solid is because it's trying to react with something that's not like a piece of metal on its own. In this beaker right here, there was Fe2 plus and Fe3 plus. There were a couple of ions sitting in this beaker. This would have been the anode electrolyte, which would be like the solution down here. In this beaker down here, there would have been some Cr2O7 and some H pluses. And then this guy right here was made out of carbon solid as well. I stole this example from my Chem 30 class. It involves some chemical reactions that aren't on your table, but I thought we could still do it anyways. So even though Fe2 plus and Fe3 plus might not be on your table, and this Cr2O7 and H plus may not be on your table, we'll try it anyways. So, okay, so that means that this guy up here was your cathode electrolyte, and then carbon here is your cathode itself. Which way are the electrons going then? Towards the left or towards the right? You're right, yeah, it's going towards the right. So Jason, you were right. How do I know that? Electrons go from anode to cathode. I memorized that it's from A to C. From anode, this guy right here is your anode. Electrons always go from your anode to your cathode. Which means that this guy right here better be your negative pole, and this guy right here better be your positive pole. That's kind of your battery. What should end up happening in this one right here is that this guy's going to lose electrons. Now, I wouldn't expect you guys to know this because you don't have these formulas in your data booklet, but what's going to happen is Fe2 plus is going to lose an electron and turn into Fe3 plus. That's what's happening over here. Fe2 plus has a 2 positive. To become 3 positive, it must lose an electron. So that's what's happening over here. And then over here, those electrons are going to get picked up by that hydrogen and probably turn into hydrogen gas. So, in the meantime, whatever the heck this thing is, that device is going to run on the power you make from it. It's brilliant, actually. Okay, if a voltaic cell is able to cause a spontaneous reaction, it causes a chemical reaction. But it's actually also possible for a non-spontaneous reaction to occur. We can actually force reactions to happen if we add electricity. And this is called an electrolytic cell. That's what I want to talk about for the next little while here in my remaining pictures here. What I've talked about so far is called a voltaic cell, named after Alessandro Volta, which is basically a battery. And a battery converts chemicals to electricity. Makes sense. You guys have seen that before. Chemicals are being converted to electricity. Right? However, there's actually the opposite kind of cell. It's called an electrolytic cell. And it's the sort of thing which causes electricity to turn back into chemicals. This is actually, I'm really glad you have this here to use as an example. When you guys use your cell phones, the battery acts as a battery, and it's called a voltaic cell. But once the battery's dead, we'd be done, right? But here's the cool thing. These rechargeable batteries, you go recharge them. If you plug them into the wall, plug them into electricity, you can actually cause the exact reaction you just had happening going this way, you can cause it to go back the other way. So if the electrons were supposed to go from here to here, and now your battery's dead, if you add electricity, you can actually reverse the reaction and recharge your battery. That's called electrolytic. Does that make sense? So the basic concept here is that, like I highlighted here, voltaic takes chemicals, makes electricity. Electrolytic takes electricity and remakes your chemicals. Hence the fact that your cell phone doesn't just have a one-time use and then dies. You get what I'm saying there? So, well, then it would be a waste of $700 iPhone, right? So here's the key to this one then. There has to be an outside power source. Okay? If you use your outside power source, like energy from the wall, or from just electricity, right, from your pocket juice, whatever this thing here is, then you can recharge the battery inside there. So here's a chart that kind of explains the similarities and differences between the two. The basic difference I need you guys to know is that a voltaic cell is what we would consider spontaneous. When you look at your reactions on the list there, it always goes like the winner is the one who steals the electrons. Well, once that reaction's done, in order to do the recharging batteries, the recharge one, it's actually a non-spontaneous reaction. It actually goes the reverse order. So the lower one on the table is actually the one that takes the electrons off the higher one. So you use your table in reverse. If we talk about one of these ones here. Other than that, everything else is actually still the same. Anodes and cathodes are still the direction of your electrons. So here's a couple of pictures of these then. Here's the voltaic cell, just like I showed you. This would be an example of an electrolytic cell. You're basically going to attach batteries to it, and because you're forcing the electrons to go, you know how I was mentioning that example about how sometimes the cell becomes too polarized? There's too many electrons, so why would more electrons want to follow the electrons? Well, if you're using electricity, you're forcing them to go against their will anyways, so you don't really have to worry about having two beakers. You can usually just use one beaker. So here's a good example of how we can use an electrolytic cell. It's called electroplating. You guys ever heard of electroplating? Anybody have like a vehicle that has like chrome on it? Like how there's like a chrome bumper or a chrome hubcap? You ever heard of that before, right? Essentially what they do is they take a piece of metal, and on the very, very outside surface of the metal, they coat it with just like a couple of atoms deep of something precious like chromium or gold or silver.
Like gold-plated? Gold-plated,
yeah. This is a good example of a spoon that's going to become silver-plated. Here's what you do. You take a hunk of silver, you take your spoon, and you put them both in the same beaker right here. And then you attach a battery to it. Well, the battery forces the electrons to go around the circuit. Because the battery is essentially electron flow, right? Then there's a whole bunch of electrons sitting over here on the surface of the metal. And this silver right here, this silver lost all its electrons, so it turned into silver positive. Well, now there's a positive silver just sitting right here. And there's electrons sitting over here. It then reattaches itself, but now it's on the surface of the spoon, and you now have a silver spoon. This is really clever. Silver used to be made of silver positive and an electron. Can you close the door, please? Thanks.
No, because you're loud.
Yeah, grade 8s.
Well, most of the grade 8s are grade.
Oh, grade 7s.
Grade 9.
Grade 9s. Okay. So you know how silver, really there's a positive and there's an electron in the silver. The electron goes through the circuit this way because the battery forces it to. The silver positive goes through the solution, and then they reattach. So it's like they were together, they separate, and then they reattach themselves, and it actually ends up coating the spoon with silver. It's actually really smart. So that's what I have described in this little bit right here. Here's your battery. Here's your hunk of silver. The electrons are going to go through the battery like so, and there's going to be a bunch of electrons over here. In the meantime, your silver disintegrates into silver plus, but that silver plus says, hey, there's electrons over here, the ones I just lost. And it reattaches it over here, and it silver plates it. I also want to try this on Thursday. I'm going to try to silver plate a penny. So what we're going to do is we're going to take a penny, and we're going to attach silver to it. And then it used to be worth 1 cent, and it'll be worth like 2, because there'll be silver coating the outside of it. Does that make sense?
Copper.
Yeah. I've also copper plated a key before, so we'll try that on Thursday in our notes. So.
Will you able to still use the key?
Yeah, it's just what ends up happening is it's a very thin layer around the outside of it.
Because whenever I think of like that kind of chemical reactions, like the battery stuff, it's like all clumps.
Well, it depends on how well it works. Sometimes it does become really clumpy, and then it doesn't coat it smoothly. But if you coat it like say just one layer at a time, kind of like painting. If I just do it like paint the whole surface, let it dry, paint again, let it dry, then it's very even and uniform. Whereas if I just took the paint can and just splashed it at the wall, it's kind of the same sort of concept as electroplating. So, what's that? Try to electroplate it? It might not work very well because in order for this to work, you have to attach electrodes to it using metal clips. It has to be made out of metal, and your spinner is made a lot of plastic. And plastic doesn't really hold electrons the same way. So we can only electroplate the metal part of it. So, anyway, here's another picture, if you guys get the concept here. The electrons are the little red dots. They're going to get sucked through the wire by a battery, and then these guys over here are missing the red dots. Well, they now go over here, and hey, look, those red dots again. They attach themselves, and then if they do it nice and evenly, it basically gold plates or chromium plates of metal. So what ends up happening then is it makes a really cheap metal be on the inside, and then a precious, valuable metal on the outside. And so you think, hey, I have a spoon made of gold, but it's not entirely gold. It's just like 10 atoms thick of gold. Right? If you were to scratch the surface, you might see that it's kind of cheated. So, there's another thing you can do with these things. You can also use them to produce some metal, some non-metals. This one's really clever. If you want to produce chlorine gas, which granted you probably should never do because you guys know what chlorine gas was used for. What was that? World War I and World War II, they used chlorine gas to like gas people. Yeah, mustard gas kind of thing. Yeah, you don't actually want to produce chlorine gas, but hypothetically, if you did for scientific purposes, you could actually get it from just salt. What you'd do is you'd take NaCl, salt, and you would heat it up. You'd superheat it and you'd melt it so that it's molten, like it's liquid. Then as a liquid, you'd put in a couple of electrodes right here, and then you'd run some electricity through it. And what would happen is over here, the chlorine version of it would lose electrons. This chlorine right here, see how chlorine's supposed to have a negative on it? It would lose its one negative electron, and it would form chlorine gas. And then over here on the other side over here, the electron would get picked up, and the sodium positive right here would then pick up the electron, and it would actually make sodium like solid. Like that's like the chunk of metal I threw in and we had the explosion from. So this would actually be very dangerous because on one side you're producing very toxic chlorine gas, and on the other side you're producing sodium metal, which if it comes in contact to water with could explode. So
let's do it.
I'm not going to do that.
Just have the fume hood on.
Yeah. So here's another thing you can do. You can refine metals. You could have like some copper right here that's like over here that's impure. And what you end up doing is you strip away the electrons from it, and then the impure copper ends up disintegrating into pieces. Well, if it's not actually copper and it's some sort of other stuff like, say, like lead, it kind of falls down the bottom as like some sort of sludge. But then the actual copper 2+, in the same way, it comes over here and reattaches itself to the other side, and now you have a pure item. So here you have something impure, rip it apart, get rid of the gross stuff, and then reattach it back together over here. Electrolysis is another thing you can do where you can produce bubbles, but I'm going to move on because I think you guys I've lost you here. So, summary of our day. 2 types of cells. Cells are not biology cells. Cells are batteries. Okay. Can you give me like 2 minutes here, and then you can make bracelets out of paper? Okay, 2 types of cells, voltaic and electrolytic. A voltaic cell is like a battery. It produces electricity. For it to occur, you have to have 2 beakers, 2 pieces of metal in them called electrodes. You have to fill them with liquid. Those are called electrolytes. And then one of the 2 pieces of metal is going to steal the electrons from the other one. Okay. In the meantime, you can run a current through it, which we'll try on Thursday. The other type of cell is really not a battery. It's like what happens when you recharge a battery. You're going to use electricity to cause something else to happen. And so usually the basic premise is, over here you're going to steal the electrons from this guy over here. You're going to force them through the wire using your battery. This guy over here is going to disintegrate into pieces. Well, those pieces can then reattach over here, and then you can plate something, or you can make a purer metal. Does that make sense? So, okay, we'll try this so you can actually try it on Thursday. I need for you guys to do some practice otherwise, though. So if you haven't finished your first assignment or the first couple labs, get that done with so that you can start on your second assignment, because the second half of the unit is all just theory of definitions. You need to know anode, cathode, oxidize, reduce, oxidizing agent, reducing agent, electrolyte, like all these definitions. It's more of a memorization of that part. So, okay, I'm done. Now you can make your bracelets. You guys have any questions? Okay, you got about 15 minutes left today. Tomorrow's a work day. Please try to get caught up, okay? Because I know some of you are falling a little bit behind here. Sound good? Yep. Okay, enthusiasm mediocre. Okay. Let me know how I can help. Enthusiasm.